Hi, and welcome to this short lecture where we learn about global navigation satellite systems, which are a very useful tool for Earth sciences. In ancient Egypt, Eratosthenes was the first person to calculate the circumference of the Earth after he noticed that the length of the shadow varies when observed at the same time but at different locations, or more accurately, at different latitudes. It has to be mentioned that Eratosthenes was also the first one to make use of an object outside the Earth to measure something on our planet. Thus, he can be seen as a pioneer of what would nowadays be called space geodesy. This branch in science includes measurements for determination of the form and dimensions of the Earth, the locations of objects on its surface, and parameters of the Earth's gravity field. It makes use of both artificial satellites as well as natural objects in space. Those objects can be either in the proximity of the Earth, for example the Moon, or almost at the outer edge of our universe. Among space geodetic techniques, global navigation satellite systems, or GNSS, are those having the strongest visibility in daily life. I guess you have heard of the Global Positioning Service, GPS, which is the oldest and most prominent system. At any given time, there are at least 24 active satellites orbiting over 20,000 kilometers above the Earth's surface. Satellite orbits are designed in a way which ensures that at any time and location on the Earth, at least 4 satellites can be tracked. All GNSS satellites transmit in L-band, which is the frequency range between 1 and 2 GHz. So how does a GNSS receiver calculate its position then? Well, each satellite sends a special signal and adds information at which time it was sent. This is called the transmission time. The receiver catches the signal and checks at which time it was received. This is called the receive time. The difference between the receive time and the transmission time must be equal to the time it took for the signal to travel from the satellite to the user. As electromagnetic signals travel at the speed of light, we simply multiply the travel time with the speed of light, and we get the distance between the satellite and the user. Fortunately, GNSS signals are designed in a very clever way, which tells us also where the satellite was when it sent out that signal. The 3D coordinates of the satellites can be used to determine the position of the receiver. However, the distance between a single satellite and the receiver doesn't give us our position. But if we measure the distances to 3 satellites, we would be able to determine our position exactly as a set of 3D coordinates. There is still a problem though. The clock inside a GNSS receiver is not synchronized to the time used in those of the GNSS satellites. As the clock of the receiver is slightly offset, the measured distance is not equal to the physical distance. We need to include a value that equals t times the speed of light in order to get the corrected distance. We can write the equation for satellite 3D coordinates where lowercase x, y, z denote the known position of a satellite, called a here. Capital X, Y, Z stand for the location of the receiver, that is, the 3D coordinates we are looking for. If we move t times c to the right side, we would then get a relation between what the receiver measures and what we need to solve for. But as you can see, we have one measurement and 4 unknowns. Suppose we can observe 4 satellites at the same time. Let's call them A, B, C, D. We will then get an equation system which has as many equations as we have unknowns. The system is not linear, but there are ways to solve for receiver position and the timing offset. This means as long as we track at least 4 satellites, we can determine our position and, as a side effect, get the time offset between the receiver clock and the time of the GNSS system. In its very basic observation mode, GNSS positions are precise by about 1 to 3 meters, which is sufficient for car, ship, or airplane navigation. Other applications, in particular earth sciences, need higher precision, which can only be achieved by special observing techniques. One of those approaches is called differential positioning and works on the idea that the position of one static receiver is known and we only measure the relative travel time of the satellite signals with respect to that station. As long as the distance between these two stations is not exceeding a few tens of kilometers, almost all distortions that degrade GNSS positions, mostly caused by the atmosphere, cancel out. And we are able to obtain millimeter precise positions relative to the position of that reference location. This works even if the receiver is moving. The second receiver is in that case then referred to as rover. If we put GNSS receivers at different locations around the globe and start designing a network in which we can compute these relative positions, we will then be able to take benefit from the relative positioning technique while still obtaining millimeter precise positions. GPS is not the only GNSS, and there exists also the Russian GLONASS system, as well as China has started to build up the so-called BeiDou system, which is expected to be completed in the year 2020. The European Union's Galileo system is scheduled to be fully operational by the year 2020 at the earliest. And other countries have started to build their own systems that increase the number of available satellites in certain regions even further. Also, as a GNSS receiver needs only 4 satellites to determine its position, we already have now 10 or more satellites available at any time and location. And the number is expected to increase even more, making GNSS more precise, robust, and reliable for commercial applications as well as for scientific tasks like monitoring our planet. Thanks for following this lecture and see you next time.